in planetary exploration, we have big problems. Not enough time to get the information back we need to look at other worlds, Earth-like worlds, like Mars, like Venus, like outer planets such as Saturn, at the kind of scales we're used to seeing for our own planet, to use them as the basis for comparison. So for me as a scientist, I'm excited about not only more data, always good, but I'm also interested in using laser communication as a way of ranging to things, figuring out how the dynamics of these objects, from small asteroids that could collide with Earth, or we may visit with humans, to planets like Mars, where weather systems and climate systems respond like those on Earth. And we need the ability to make measurements of very small changes. So laser communication opens up some of those things in the scientific domain.
The idea is that a future satellite, instead of being a science experiment or an engineering experiment, can instead use optical communications as their mission critical, their way of getting the information back to Earth. And that's what this project is proving. On a satellite in geosynchronous orbit, we're putting 2 telescopes. They're optical terminals, and basically we're going to transmit signals to one ground station and relay to another. So to give you an idea, assume we have a ground station in Southern California. So we have a video image or a file that you want to send. You'll transmit that signal up to the geosatellite. It'll receive it on the telescope, and then it sends it over to the second telescope, and it lasers it back down to the ground, let's say in White Sands, New Mexico. And so what we're trying to prove, what we really like to do is to move this technology forward so that another spacecraft could communicate with the geosatellite. And that's the next step after this. But in order to save costs and try to move technology forward, we can simulate all of that with just the 2 ground terminals on the ground. So that's one reason that we have this configuration. The second reason is when you're using optical communications, clouds are a problem. So we do not know how to burn through clouds. So when a cloud comes up and blocks that path, we have to do a handover. So just like you're in your car and you're using your cell phone and you're driving along, and at some point you get too far, the cellular system has to move you to another base station. The same thing's happening here. So we're out in geosynchronous orbit, and we can send information down to, say, Texas. The minute a cloud or something shows up, we'll automatically switch over to California. And so we're proving out the concepts and how to do that so that a real mission can really make use of it.
So the first challenge I want to demonstrate is just the challenge of pointing the narrow laser beam to the target on the Earth. So if we have a terminal located in, say, Southern California or New Mexico or someplace, then just the movement of the laser at such a narrow beam is something that we need to keep from happening, otherwise we'll be off target, we won't be able to communicate. So on board a spacecraft, there is just natural motion. There are some moving parts and things that happen on a spacecraft, and all of those vibrations, even the smallest vibration when at a great distance, will lead to trouble pointing the laser. So one of the biggest challenges is just trying to keep that laser pointed directly at the target that you're trying to point to.
So what we need is hundreds of megabits a second to maybe a billion bits a second, a gigabit. These are the kind of video rates we're used to seeing when we watch the Super Bowl and see those great sports games. That's within our grasp with laser communications at Mars, likewise at planets like Venus, our sister planet, and even extending far out to places like Saturn. We can imagine increasing the flow of information that now is dribbling back from our brilliant mission Cassini, increasing that by a factor of 10 to 100 as we explore the beautiful system at Saturn. So let me give you an example. Imagine dialing your garden hose to have a trickle of water trickling out and having to be really smart by where that little dribble is going to water your plants or your tree. Imagine instead having a continuous fire hose or even an episodic fire hose. Whoosh! You can barely control it like a firefighter might have. That's the kind of mental picture I would use. The same thing is true of using laser communications as a ranging tool for science to figure out the dynamics of objects that might be extremely unique. Small objects tumble and roll, and they rotate in ways that are not like we're used to for big planets. We need to measure that stuff, and laser communication can increase our ability to measure it from today's rates by a factor of 10 to 100 better. And that's the kind of leap, a paradigm shift that in science we live for.